Okay, so welcome back to the second portion of the class. So now that we learned about the properties of the real networks in our face-to-face class, today we're going to talk about random variables and random graphs and what does that entail in terms of their properties. So before we introduce random graphs, we need to review the idea of random variable, which we already talked about briefly in the first session. Because random graphs are just built entirely on this whole concept of random variable. So, a random variable, by definition, is simply a way to assign numbers to the outcomes of some particular experiments. So, the idea is that we would like to reason about some uncertainty in a mathematical way. So let's start with a very simple possible example, and where our experiment is just a simple tossing coin here. So the coin has, of course, in a fair experiment or a fair coin toss, it has two possible outcomes, a head and a tail, and these outcomes are not numerical by themselves, but we would like to somehow encode them in order to get some numerical values for some what is the most probable outcome of head or tail. So in this example, for example, we define a random variable x to be representing the observed face. And so a head is mapped to 0, and the tail in this case is mapped to 1, as we are showing as x1 and x2 possible values for the random variable x. So this numerical encoding it might seem arbitrary, but once you chose it, it can allow us to work with probabilities and expectations, which is the next concept here. So in this case, our sample space of x is only two sets of values, either 0 or 1. And so if the coin is fair, which it is in this slide, the probability of the two outcomes is just half each, right? So we have only two outcomes, and so 50% to get to have a to have a tail versus another 50% to get a head after the tossing the coin in this case. So for this coin toss example, the expected value of x is nothing but multiplying each possible value by its probability and summing the results, right? So in this case, the value x is equal to 0 times the probability of x being 0, which is 0.5, plus 1, which is the value of getting a tail, right? Times the probability of getting a tail, which is 0.5, and therefore our expected value x is equal to 0.5, which means that if we toss the coin many times and we repeat the experiment many times, then the average value of x will approach 0.5, and that's exactly what the expected value or expectations entails mathematically for a random variable in this case. Now, another example, just to grasp this concept well. So if you pick a student at random in this class, right, and we say that, well, x is equal to 1 if the student attended class today, and x is equal to 0 if the student is absent, right? So we can immediately ask, the question is, what would x is equal 0.8 mean as an expected value? So this simply means that, well, on average, right, the student has showed up in class about 80% of the times, regardless of today's presence, right? So the expected value is nothing but a fraction or just a rate, not the actual observed outcome of today's experimentation, right? So expectation is over multiple trials. What can we expect as the value, as the possible outcome of in general or on average? Okay, so let's move on to another example in this case, which is the balls inside of a bag example. So let's say that in our bag we have two types of balls. We have blue balls and red balls, right? So in this case, let's say that we have two balls that are blue, or three balls that are blue, and the rest of them are just a red. And in this case, let's just assume that our red balls is only one of them, just for the sake of simplicity in this case. So here, if you were to encode that in terms of random variables, then x can easily be is equal to 1 in case the ball that has been drawn is blue, right? And the random variable here, x is equal to 0 in case the ball is red that has just been picked up from the ball from this bag at random, right? So in this case, the random variable it just embodies our ball picking from the bag, right? So that's what x in this case means. And so by default here we have 5 type of balls, right? So we can easily compute what's the probabilities of x from the actual values. So probability of x is equal to 0 is equal 1 over 4. We have 4 balls and one of them is red. And the probability of x is equal to 1 is in this case 3 quarters, which is 75% of the cases in this case. Now, if you were to compute the expected value of x, right? So on average, what would be the value? It's simply x, it's simply 1, right? For the value for x is x is equal to 1 times the probability of x is equal to 1 in this case, which is 3/4 of the times, right? Plus 0, which is the ball being red in this case, times the probability of being red in this case, which is 1.4 in this case. So on average, the expected value is nothing but 3/4 in this case. So which is equal to 0.75, right? So on average, we are more likely to get a blue ball versus a red ball in this case, and that's what the probabilities means in this case. So adding these together, our expected value of x is equal to 0.75. Now, the expected value, and this is just a disclaimer note here, is that it does not really mean that we expect to draw 1/4 of a blue ball, right? We cannot say that. But instead, it simply means that if we repeat this experiment many times, then the average value of x will approach 0.75 in this case. So in other terms, about 25% of the draws will be red and 75% of the draws will be blue in this case, right? And of course, I should also add that you can do that also for variables that are not necessarily numerical, right? So for discrete variables, like let's say, or for numerical variables as well, that are, let's say, like a temperature, right? We can define a random variable x to be 1 if the temperature is greater than 70 degrees Fahrenheit, or x is equal to 0 if the temperature is strictly less than 70 degree Fahrenheit. So it does not have to be a discrete outcome like blue or red or head or tail, right? We can also encode the discrete the numerical variables by just defining what is this discretization of that variable in terms of intervals, right? Greater than 90 or less than 70 could be the outcome of our random variable, which encodes the temperature in this case. So the temperature itself is continuous, but we can compress it into a simple yes or no variable, like if the temperature is greater than 70 or less than 70 in this case. So this just shows that random variables often have this ability to simplify the reality, and it also enables us to encode as a modeling choice in this example. All right, so let's just go back to my previous slides here. Okay, so now let's look at the bias experiment to strengthen our understanding. So in this experiment, we're supposing that we're having a coin that always lands on the tail, right? For just like the case of this shuttlecock in this in the board. So we define exactly the same random variable x, just like the previous slide, where the head is embodying zeros outcome, and the tail is embodied by 1, a value of 1, x is equal to 1. But here the difference is that the probability distribution is changing, right? So the probability that x equals to 0 is 0, and the probability of x equals to 1 is 1. It's always it's a total and fair extreme case of the experiment. So there is no randomness left in the outcome, but we still describe it using some random variable x, as you see here in the slide. So if you were to compute the expected value, right, using the same exact formula that we showed in the previous slide, this is nothing but it is the sum of each outcome times the probability of the outcome paired in this equation. So the probability of x being 0 times 0, right, and the probability of x being equals to 1 times 1 as being the outcome. And you could see that the expected value here is equal to 1, meaning that in this extreme example, uh, having a 0 value is impossible, and therefore we should always expect 1 as being the answer and being the outcome of the experiment in this case. So this example is useful because later, when we talk about random graphs, we will see that edges that appear with probabilities of 0 or probability of 1 or something in between have the abilities to be encoded using the same expected expectations of the random variable of having an edge between two nodes later on. Okay, so now we're moving on to a little bit more exciting stuff, and the Erdos and Rainey random graph model is our next topic here. So we move on from the coin tosses to graphs. And the Erdos-Rainey random graph model is just one of the most, I would say, naive or simplest, and probably also the most fundamental random graph model. It was introduced by these two guys. So we have Paul Erdos and Alfred Rainey, and that was in the 60s. And the idea is that in any graph G that we encode using G, in the subscript NP, formulation, right? So we start with a fixed number of nodes n that we might have in mind, and for every possible pair of nodes, we decide whether an edge will exist or not exist, and we do that by just performing a random experiment, like the coin toss example in the previous slide. So more specifically, each possible edge appears independently and identically distributed, just like it's written here. So we call this property as being IID, right? With probability of P. So you can think of this as flipping a biased coin for every pair of nodes. So with probability P, the edge exists. With probability 1 minus P, it does not, right? And the reason why we call it independent and identically distributed is because each experiment is independent from another one in this case. So we can generate a random graph using the NP formulation, right? So having n nodes for each pair of random nodes, we will decide whether the edge exists or not with the probability of P, right? At random, we will just pick, let's say P is equal to 0.3, right? Then there is 30% chance that that two random nodes will have an edge that exists in between them. Now, there's also an alternative formulation, G and M, right, which is the second bullet point in this case. And in this case, where the graph has exactly n nodes, but here what's the difference is that M is the edges chosen at random, right? And this is uniformly at random as it is formulated in this case. So while the two models are different, they behave similarly, right, for the case of large graphs. But here we just say specifically that, hey, we would like to get n nodes and m edges. You can randomly distribute them, but I'm not telling you in terms of probabilities in this case. It's just a different way of generating a graph at random here. Okay, so now the next slide, here slide 18, tells us what's the role of the probability P, or the peak parameter in this case. So we all know by now that P controls how dense the graph is, right? You could see with P is equal to 0, which simply means that we have 0 chance of getting any edges in between the graphs, in between the nodes of my graph in this case. So if P is very small, close to 0, the edges are rare and the graph is quite sparse, right? So for example, p is equal to 0.1 simply means that we have only about, in this case, 6 edges across all these nodes here. As we increase the p, of course, the graph becomes more and more denser in this case. So p plays the same role as the probability of heads or tails for the case of the coin toss example. It just controls how likely an edge will appear in the graph in this graph example here. Okay, so now we're going to move on to talk about the randomness here process. So one important point that kind of causes sometimes confusion is that if we fix n and p, it does not uniquely determine the graph, right? So even if we fix the number of nodes and the probability p, the graph is still the result of just a random process, right? Because with the probability of p, I might get an edge between the nodes or not, but if I repeat the experiment, I might get a different outcome with the same exact probability. So each time we generate a graph using the same parameters, n and p, or N and M as well, which is the second Erdos and Rainey graph generation algorithm, we may still get different structures. So some graphs may have more edges for the first case scenario with the probability of p, right? So in this case, if we're using probability of or g and p, then sometimes we might get m is equal to 8 or m is equal to 7. Again, m is equal to 8. It depends. It really depends on the randomness of the process over here. And this is exactly like the tossing the same coin multiple times and getting different sequence of outcomes, right? So sometimes I might get 5 faces out of 10 or even 6 faces out of 10 experiments, right? So that's exactly what it means here. Of course, it's not the same case for the second more deterministic algorithm of fixing n and m, but still you're getting a different network topology, right? If you're using a network with m edges, I can choose different random nodes to put the edge in between them in any graph example. Okay, so now let's move on to more technical stuff, and number of edges as a random variable is our next topic. So if we just treat the number of edges as a random variable, and in this case we call it m, which is our variable here, then this m can simply denote the number of edges in a graph generated using some, let's say, g and p or g and m, or g and p algorithm of the Erdos Rainey case here. So the maximum possible number of edges in an n-directed graph with n nodes is n choose 2, right? Like the formula which is here at the very end of the slide. So maximum possible number of edges is n choose 2, which is equals to n times n minus 1 over 2. And if you were to try to understand what's the logic behind this, is that each choice of 2 nodes gives us 1 possible edge, right? So therefore, the maximum number of edges is the number of ways we chose those 2 nodes, right? So there are multiple ways we can choose these 2 nodes from n nodes, right? So this combination is telling us what that the maximum number of possible edges that we have in a given graph. So it's always going to be n choose 2 for any graph here. So each of these possible edges is included independently with a probability of p, right? Which we use here next. So the total number of edges follows some binomial distribution. We say that it follows a binomial distribution, right? So with the probability of p, we will get an edge or not, just like we will get a face or not for the case of a coin toss. So it's a binomial distribution in this case. So the probability that the graph has exactly m edges, right? So p of m is equal to, if we want an exact number m of edges using that probability p, is nothing but e choose m, right? Which is in this case the maximum, using the maximum number of edges. If we choose m from them, right, which is Pm is equal to M, times the probability of the edge existence, right, which is P, M times P times P times T M times, because we want to have M edges in our graph, times the probability of not getting an edge in the remaining edges that do not exist in the graph, which is 1 minus P times E minus M, which is the remaining nodes that do not have any connections in between them here. So in other terms, probability of M is equal to M here is nothing but E choose M times P to the power M times 1 minus P to the power E minus M in this case. Okay, so that's the expected number of edges that we just talked about in the previous slide. Now, the expected value, right? So the expected, so here the probability of generating one specific number of edges is what we talked about. Now, if I want to know on average what's the expected what's the expected number of edges that we should have, it's exactly the maximum number of possible edges, which is E that we computed in the previous slide, times P, right? P is the probability of edge existence in a given graph. So in other terms, P times N choose 2, which is all the possible ways of choosing 2 different nodes from the graph of N nodes in this case. And if you just copy this formula that we just computed in the previous slide of N times N minus 1 over 2, then we get P times N minus 1 over 2. I'm not going to ask you about these formulas, particularly on how to deduce them in the exam, but I might ask you, hey, what's the maximum number of possible edges in a given graph? What's the expected value of a given edge numbers in a given graph if you're using the second Erdos-Rayleigh random graph generation process? Okay, so we already mentioned in the previous slide about the binomial distribution, which is also the case of edge existence in between 2 nodes, right? It's just like the Toyn cost example. And if you look at this particular figure on the right hand side, you should see your binomial distribution with different probabilities and ends. And you should see that, well, with higher probabilities, of course, we should see a higher number of expected value, which is also the mean of the distribution in this case. Of course, here we're talking about different graph size, right? So with a greater or with a graph of or larger graph of n is equal to 40, then our expected value naturally is higher, even with a probability of 50%, which is less than 70% for the case of the green binomial distribution here for n is equal to 20. So if you just compare the blue and the red, right? The blue and the green graphs over here, or distributions in this case, because they do have the same number of nodes, which is n is equal to 20. You'll see that the expected value or the mean of the green distribution is way higher, because the probability of getting no edges between my nodes is 0.7, which is higher than 0.5 for the case of the blue binomial distribution in this case. Okay. All right. So the expected value now what's the expected value in this case? So the expected the probability in this example, the expected value is nothing but n, right, which is n number of nodes times P, which is the probability of getting an edge in between the two random nodes in this case. So the probability of getting the number of nodes in this graph is nothing but n times P in any random graph example that you might have. Okay, so to go deeper, we now would like to focus on a single edge. And to do so, we can define a Bernoulli random variable, right? That indicates whether some specific edge exists or not in between the nodes. So if the edge exists between 2 nodes I and j, then the variable is equal to 1. Otherwise, the variable is equal to 0, which is dij is equal to 0 in our slides. So the probability that this variable dij equals 1 is p, and the probability that it equals 0 is 1 minus p, right? So the expected value in this case of the variable of our variable dij is therefore is equal to p. Why? Because, well, that's the probability of edge existence in general, and more specifically for the case of two random variables I and j in this case. Or in other terms, it is nothing but 0 times 1 minus p plus 1 times p, which is equal to p in the case of dij. So the expected I would expect on average that if you pick two random nodes in a random graph I and j, that p they will have an edge with a probability of p in this case. So the degree of a node is the number of edges connecting to that node. We already know that from data structures. And mathematically, the degree of a node can be expressed as the sum of all the possible edges connecting to that node to the other. In other terms, now that we computed the expected value dij, which is equal to p, now we could compute what is the degree of any node I that I have in the graph. In other terms, how many edges connect to that node, right? And it is nothing but the sum of all the possible of all the edges I and j, right? With j being all the other nodes that exist in the graph, which have a value of 1, right? Because a value of 1 simply means that there is an existence of an edge between the two random variables, random nodes I and j in this case. Okay, so what's the expected value? So on average, in other terms, so if you pick one node at random from a random graph, what is the expected value of their degree, right? So that's what the question that is asked here, and that is answered by this by the last portion of the slide. So the expected degree of a node I is nothing but the expected value of this sum that we have over here. So if you pick up the sum outside of the expected value over here, right? Because the sum can be taken outside of the brackets in this case, and you pick and you replace the expected value of dij, which we already computed in the previous slide, which is equal to p. It is nothing but the sum from j is equal to 1 all the way to n minus 1, right? Because n minus 1, because we don't count the node as itself, which is I in this case. So we don't count the self loops or self connections, which is essentially an edge with the node and itself, right? And in this case, this is nothing but n minus 1 times p as the expected value in this case, right? So p times n minus 1 times is what should be on average the degree of any random node that you pick up from your random graph here. Okay, so now we move on to another random variable here. So beyond the expected degree, we can still ask questions about the full degree distribution, right? So in a random graph, the degree of a randomly selected node follows a binomial distribution, like we showed in the previous slide. And that's because it's the sum of the independent Bernoulli trials corresponding to that, to some possible edges. So now this distribution is peaked around the mean, as you could see here, which is the expected value as well here. So n minus 1 times p. This behavior is different from what we observe in real world network, right? So because in the real world, we saw that the degree distribution often follows a heavy tail, or we also call this a power law distribution in this case. So all right, so here what you're showing in the slide is what's the d as being a random variable, and that's representing the degree of any selected node having a particular value of d in this case. So the probability of d having a value of d of small d in this case is nothing but n minus 1 chose D, right? So from n minus 1 nodes, I need to choose D. In other terms, the from if you pick a node that's random, what's the probability that that node has a degree of D, right? So it has n minus 1 maximum possible number as the degree of that node. I can have a connection with everybody in the graph, and in that way it's n minus 1, except for myself, of course. That's why we say n minus 1. But we chose D from this maximum possible number of neighbors that exist in my random graph times p to the power d, right? P times p d times, and that's the probability of having an edge with the other neighbors d times the opposite side as well, which is 1 minus p, or the probability of not having edges with the remaining neighbors that I don't have a connection with, to the power n minus 1 minus d, right? So there are n minus 1 minus d nodes that I'm not connecting to. D of them I'm connected to, and there are actually n minus 1 chose 2 ways to pick those nodes from my random graphs, right? So that's my probability of D is equal to D in this case. Okay, now the expected value of D is n minus 1 times P, right? So because the probability of having an edge between two nodes is P, and there are many, and these are all the possible neighbors that I have, or connections that I might have. So on average, I will have n minus 1 times P, probability of having an edge with everybody else in my random graph. Now, if you just look back few slides, right, and you try to find a connection between the expected value of M and expected value of D, if you look at the expected value of D, which is n minus 1 times P over here, and you go back to what is the expected value of M over here, you'll see that, well, it's also in terms of P and N. More specifically, expected value of M is P times n minus 1 over 2. So in other terms, I can easily formulate the expected value of M in terms of expected value of D by just replacing n minus 1 times P by expected value of D over here. So expected value of M is equals to n over 2 times expected value of D over here. So if this tells us something, it just tells us that this whole process of a random graph generation is not so random, right? Because I can easily deduce one value from another one because it is quite deterministic at the end of the day. If you know n and p's n and p parameters, then I can easily know what's on average m and what's the d values in terms of each other in this slide. Okay, now we're going to talk about a different concept and more specifically about the clustering coefficient, right? So we already defined clustering coefficient as a measure which measures the likelihood that two neighbors of a node are also connected to each other. So in a random graph, the probability that any two nodes are connected with each other is P, right? Regardless of whether they share a common neighbor or not. So as a result, the expected clustering coefficient of a random graph is simply equal to P in this case, right? And more importantly, right, so the probability P is our expected value for random graph. For the case of real networks, right? The clustering coefficient is defined by this formula that we already talked about in class, and we also practiced with a few examples, and in theory it should follow some power law distribution over here. So if this tells us something, then it simply tells us that the value does not depend on the degree of the clustering coefficient does not depend on the degree of the node. So high degree and low degree nodes have the same expected clustering coefficient regardless. So which is very different from real networks, as we discussed in the prior in class in the prior slides, right? So everything at the end of the day here is kind of expected for the random graph example. In fact, there are direct proportionalities in between the expected values of different random variables in the case of a random graph, which is not necessarily the case, which is not the case for a real network. Okay, so at this point we can clearly compare the difference between real versus random real networks and random graphs here. So we could clearly see that from the previous slide that real networks are typically having a heavy tail degree distributions. They have a heavy tail or a high clustering coefficients and a very short path length, right? So that's what, in other terms, we say that the real networks are scale free, or we're talking about a small world network, right? So in other terms, if you're within a few hops, I'm able to reach anybody in the network, like we said for the case of the Facebook network, right? Uh, if you look at the random graph models, the path length is not really on the smaller end. In fact, it is in terms of n, which is O log n in this case. So it's not a short nor a long. It really depends. It's directly dependent on the size of the network in this case. So the clustering coefficient is nothing but p. It's very deterministic. It does not really have some heavy tail distribution or so. And we're talking about a binomial distribution of degree distributions, right? So there is no heavy tail. It is a very beautiful symmetric distribution that we're talking about in terms of degrees for the case of random network. So the paths as well scale logarithmically with the number of nodes, as I mentioned. This is so the figures here just shows real versus random graph. So the graph degree distribution versus the degree distribution if we were to do it for a graph that someone just generated in class, which is not really generated from a real process in the real world. Okay, so why do we even spend time to discuss random graph if we are really interested about real networks, and that's where the impact comes in when we apply algorithms in real data sets. So random graph, simple answer is that it serves as some benchmark or some null model. In fact, they can easily provide for us some simple baselines against which we can easily compare the real network. So, by understanding how they work, we can identify what's the properties of real networks, and that way we can explain also the randomness, the randomness in real networks as well. So they're also mathematically good, elegant, because they're essentially good as a starting point for developing some more realistic models, such as the small world and scale-free networks. In fact, if I have, let's say that I have an idea about some innovative algorithm that I want to try and I want to propose in my next research paper, then I can always start with a synthetic random graph that I generate with one of those processes or algorithm that we talked about previously, and see how that worked for a random graph and how does that work. And later, when I have more bandwidth in terms of memory, I can try that on a larger real network in this case. Okay, so now I'll stop sharing my screen. I will just go back to the whiteboard for one last example here. And that can be very useful for your homeworks and exam preparation later on, right? And this is just a simple example and practice where we have a network. Let's say that we have a network which has 5 nodes, right? And probability, right? So using a Erdős and Rényi algorithm of G G sub n p, I am using n is equal to 5 and p in this case being 0.3. In other terms, I have only 30% of getting an edge in between the random nodes that I have here. All right, so my first question that I have here is how many possible edges are there? In other terms, that the one we saw in the slides, how many possible? What's the maximum number of edges in between all the nodes that I have here? And the answer to this is if you use the E formulation that we have, which is essentially n chose 2, right? So n chose 2 in this case is the answer over here. So if you do the math, this is equals to n times n minus 1 over 2 is the answer over here, and which gives us, in this case, for the case of 5 nodes, which is 5 times 4, right, over 2. And if you do that, the math, it should be equal to 10 in this case, right? So maximally, we should have about 10 nodes in the graph with or 10 different degrees in between all the random nodes that I have in the graph here. Now, if I ask you as a next question, hey, can you list all the possible nodes? Then you can easily say that, well, yeah, between nodes 1 and for the case of node 1, right? For the case of node 1, I can have these are the nodes, the edges that might exist. So there might be between 1 and 2, between 1 and 3. There might be another edge between 1 and 4, and as well as 1 and 5, right? All right, so now let's do the same thing for node 2 and just remove in this case the node 1 and 2 as well. So there might be an edge between 2 and 3, another edge between 2 and 4, and finally another edge between 2 and 5 in this case, right? So that can give us already 7 edges from all these nodes here. Okay, now between node 3, there is a remaining 2 other nodes that I still did not list. So between node 3 and node 4, and another one between node 3 and node 5. And finally, for node 4, right? So the one that I still did not list is between node 4 and node 5 in this case. So 1, 2, 3, and 4 in this case. All right, so if you do the math and you count over here, then we have 4 from node 1, 3 from node 2, 2 from node 3, and 1 from node 4. So in total, we have 10 possible edges in between all those 5 nodes that exist in my random graph. So I just listed all the possible ones. Meaning that you'll flip the coin 10 times and once per possible edge over here. Okay, so now the second question is the graph fixed once we chose N and P? If you think about it for a second, if you just choose N is equal to 5 and P is equal to 0.3, then can we get, what's the, can we get always the same answers, right? So let me just randomly draw a graph here of 5 nodes. Here, and with a probability of 0.3 times of having edges in between them, then on average I should have only 3 edges, right, in between those nodes. Only 3 edges. So I can have the first topology of the network here being edges in between these 3 nodes over here. So let's just say that, well, there exist edges between those nodes over here, this node over here, node 1 and node 2, node 3 and node 4, and node 5 in this case, right? I might get a completely different topology in my second trial, right? Instead of having an edge between 3 and 5, I can have an edge between 1 and 3. In fact, it's very, very, very highly unlikely that all of us in this class, if I just tell you to draw a graph of 5 nodes and draw me 3 edges between those 5 nodes, that we will get exactly the same answer. So the answer to my question that if the graph is fixed once we chose N and P is no. The graph is random. It is not a fixed topology graph. We might have completely different networks using the same exact parameters N and P of my Erdos and Rainy algorithm here. Okay, now my last question is, will two graphs generated with the same N and P look identical, which is which is kind of like a follow-up question to the second one, and the answer is also no, because we will have completely different architectures, right? So we won't have, it's highly unlikely that N and P will give us the same graph, nor two graphs which have the same which have the same number of edges. So it's possible to have exactly the same number of edges with 0.3, but it also might be in some cases, some other person with p is equal to 0.3, they might get an extra edge, like the case that we saw in class, right? With probability of 0.6 or 0.5. Sometimes m is equal to 8, sometimes m is equal to 6, right? Okay, now I think this is the end of this today's class. I don't want to bore you with so many details. You already have a lot of concepts to work with. So next time we're going to talk about graph representation in memory. Please make sure that you understand this concept well, and you start playing a little bit with the practice series and gather all the questions for me for the beginning of next class. Thank you very much for your attention and good luck. See you next time.